Welcome to day 40 of our STL course. Congratulations on making it this far. Today we will be diving into project reviews and optimization techniques. These concepts are incredibly important as they help you define and enhance your STL based projects. You will learn how to assess your code, identify areas for improvement, and apply optimization techniques to improve both performance and clarity. So let's get started and make sure your projects are not only functional but also efficient and elegant. Before we dive into the details, let's take a look at what we will be covering today. First, we will review our STL based projects. This review will help us identify design flaws, performance bottlenecks, and areas where optimization is needed. Next, we will introduce a series of optimization techniques ranging from algorithmic improvements to memory management strategies. These techniques are critical for taking your code from functional to efficient. Finally, we will discuss the importance of code clarity and efficiency. Remember, optimizing your code isn't just about making it run faster, it's about making it easier to understand and maintain. To effectively review your projects, it's essential to have some solid evaluation criteria. These criteria will guide you through the process of assessing the quality of your work. Let's break down them. First, we need to evaluate if you have selected the right STL container and algorithm for the problem at hand. Choosing the correct data structures can make a significant difference in performance. Next, we will look at modularity and reusability. Is your code well structured and easy to reuse for other tasks? Naming conventions and readability are also key aspects. Your code should be clear and understandable at first glance. We also need to evaluate how your project handles edge cases. Does it account for all possible scenarios? Lastly, performance benchmarks are crucial. Are you using the most efficient algorithms and data structures? These benchmarks will help you identify bottlenecks in your code. As you review projects, it's important to be aware of common mistakes that can easily slip in. First, a big mistake is using manual loops when STL algorithms could be used instead. STL algorithms are optimized and can make your code cleaner and faster. Another issue is selecting the wrong container for the task. For instance, using a vector where a DQ is more appropriate can slow down performance. Additionally, using insert where emplace would be more efficient can lead to unnecessary copies. This can have a major performance impact, especially when working with large data. Lastly, it's important to be aware of complexity. Every decision you make, such as choosing a container or algorithm, has a time and space complexity. Ignoring these impacts can make your code much slower than necessary. Our fast optimization tip focuses on algorithmic thinking. The STL is packed with highly efficient, pre-written algorithms that can save you a lot of time and effort. Instead of writing manual loops, consider using the appropriate STL algorithms like binary search, countif, or transform. These algorithms are not only more concise but are also optimized for performance. By using these built-in functions, you avoid reinventing the wheel and get the benefit of well-tested, efficient code. Algorithmic thinking allows you to approach problems more abstractly, making your code both cleaner and faster. Optimization tip number 2: choosing the right container for the job. This is crucial for improving performance. Let's take a closer look at this table, which outlines the preferred containers for various tasks. For example, if your task requires frequent insertions and removals at both ends, the DQ is a better choice than vector because DQ offers constant time insertions and deletions at both ends. For tasks that require fast lookups, an unordered map is a much better choice than map because it provides average constant time complexity for lookups. And for ordered fast inserts, a set or map is ideal. These containers are optimized for the operations they support, and selecting the right one can drastically improve your project's performance. Our third optimization tip is to use emplace rather than insert when adding elements to a container. The key difference is that emplace constructs the object directly in place, which avoids creating a temporary object. This can be a significant performance boost, especially when dealing with complex objects like pairs or tuples. Consider the example of inserting a large object into a map or vector. If you use insert, it will first create a temporary object and then copy it into the container, which is an unnecessary overhead. On the other hand, embrace constructs the object in place, eliminating the need for a copy. This small change can lead to much more efficient code. Optimization tip number 4 is all about memory management. When working with vector, you can optimize performance by reversing space ahead of time using reverse M. This helps avoid multiple reallocations as elements are added. If you know in advance how many elements you will be inserting, reversing space can save a lot of time. Similarly, shrink to fit can help free up memory that is no longer needed. For example, after removing a large portion of elements from a vector, calling shrink to fit will reduce the capacity of the vector to match its size, freeing up unused memory. Proper memory management is essential for ensuring that your program runs efficiently, particularly when working with large datasets. Optimization tip number 5 is to avoid unnecessary copies. Passing large objects by value or copying them unnecessarily can severely degrade performance. Instead, always prefer passing objects by reference. And if you are not going to modify the object, pass it as a const reference. This ensures that you don't copy the object, which can be particularly expensive when dealing with large data structures. Additionally, when accessing elements from containers, make sure you are using references to avoid copying. This simple practice will make your code more efficient and less prone to performance issues. Optimization tip number 6 focuses on custom comparators and hashers. In cases where you are using custom types as keys in a set or unordered map, you need to define how these objects are compared or hashed. This is critical for performance as insufficient comparators or hashers can slow down the entire operation of the container. For example, if you are storing objects in a map, the default comparator might not be the most efficient for your data. You can create your own comparator optimized for your data type to improve lookup times and make your code run faster. Here's an example of code optimization. In the before code, we are manually iterating through the vector, checking if each element is even. This is fine for small data sets, but as the dataset grows, this approach becomes inefficient. In the optimized version, we use COUNTIF, a powerful STL algorithm to count the even numbers in a more efficient way. Not only does this reduce the complexity of our code, but it also takes advantage of the optimized internal implementation of COUNTIF, making the operation faster and cleaner. Now let's look at some real-world STL optimization case studies. In a leaderboard system where you need to maintain an ordered list of top scores, using a multiset can be very efficient. The multiset automatically keeps elements in sorted order, so you don't need to worry about sorting the list manually after every update. Similarly, in a task scheduling system, using a priority queue ensures that tasks are processed in the correct order based on their priority. Both of these cases highlight the power of STL containers and algorithms in real-world applications, where performance is key. It's now time for peer review and group feedback. Share your projects with your peers and discuss the design decisions you made. What STL containers and algorithms did you use and why? Are there any areas where you can optimize further? This is an excellent opportunity to receive feedback from others and refine your approach. Sometimes others can spot potential improvements that we might have missed. Take this time to learn from each other's experience and perspectives. To wrap up today's session, let's review the key takeaways. First, remember that your design decisions have a direct impact on performance. Selecting the right containers and algorithms is crucial for making your code efficient. Second, STL tools are incredibly powerful, but they must be used wisely. Familiarize yourself with the right tools for the job and leverage their full potential. And finally, always aim for clarity and efficiency in your code. Clean, readable code is just as important as performance, and a balance between the two is key to writing great software. Looking ahead to day 41, we will focus on mock interviews. You will have the chance to practice explaining your STL projects and optimizing in a real-time interview setting. This will test not only your technical skills but also your ability to communicate complex concepts clearly. Make sure to revise all the optimization techniques we have discussed today, as they will be useful in the mock interview. Prepare yourself to explain your design choices and optimization strategies in details.